Now that we know that Taylor and Maclaurin polynomials can be used to model functions over a short period, we've kind of talked about this in the past. We could use that to model a function over a wider period by making that an infinite degree polynomial. So like we had in the past, things like P3 only went up to degree 3, if we really wanted it to model a function at the most possible places, we generally have to let this polynomial go to an infinite degree polynomial. So we've seen from our power series before, we had our sum n equals 0 to infinity, our a sub n, x minus c to the n. Now, since this is centered here at c, generally this would be any generic power series. However, and if it was 0, that would be kind of like a generic one that's centered at 0. We generally consider someone a Maclaurin. But these are only going to be considered Taylor and Maclaurin series if we use a specific formula for a sub n. Now we saw a sub n, our formula from that series, when we talked about their polynomials, this is what a sub n was. So for either a Taylor or Maclaurin series, let's see if I get this straight, f sub n at c over n factorial x minus c to the n. Now, of course, this is our generic Taylor series. If it was centered at 0, we would call it a Maclaurin series. So this is also a very helpful way to model a function. However, to do this, we have to write out a bunch of terms and see if we can come up with a pattern. Let's try this. Find a power series for f of x is equal to sine x. Let's center this at 0 just for the ease of it. So we're going to do the exact same thing we did for a Taylor polynomial. We're going to start writing out derivatives and finding these constants. However, we don't know when to stop here. That's going to be the tricky part. So I'm just going to start here. Let's do our f of x is sine x, f prime of x is cosine x. And I'm going to do several of these for a while. Let's go down to 4, I guess. There's 3 there. That's going to be negative cosine x and 4. We may have to do more. You'll see that we might have to do a derivative that's going to be sine x. All right, now we want to evaluate these at our center. So at c equals 0, so f of the sine of 0 is 0, f prime of 0, cosine of 0 is 1, f double prime at 0, sine of 0 is 0, f triple prime of 0 is going to be negative 1, and the fourth derivative at 0 is going to be 0. All right, let's start, let's figure out what these are. So that means that a0 is 0, a1 is going to be 1 over 1 factorial, right? I'm just plugging it into our a sub n's. A2 is 0 over 2 factorial. A3 is 1 over 3 factorial. A4 is 0 over 4 factorial. I missed a negative. Sorry, that was negative. Okay, so if we take a look at these and we write out our generic polynomial, we know here, I'm going to just say f of x here, is going to be, let's do a0 plus a1, our center is 0, so that's just x, a2 x squared, a3 x cubed, on out forever. So let's plug in what we do know. So f of x is equal to 0 plus 1x plus no x squared minus 1 over 3 factorial x cubed plus 0. Well, by looking at this, I'm going to add some more to that line, but if we look at this, we really didn't get much out of that. All we got was x minus 1 over 3 factorial x cubed. That's really not enough for us to establish a pattern to try to put this back into a power series. So let's see if we can establish what's happening here. Well, look at our derivatives. They go 0, 1, 0, negative 1, 0. That's back where we started. So guess what? The next one would be 1, so on and so forth. So here we have on the top 0, 1, 0, negative 1, 0. So a sub 5 should be 1 over 5 factorial. A sub 6 would be 0, I'm going to stick it over here. A sub 7 would be what? We're at 0, 1, 0, then would be negative 1. So that's negative 1 over 7 factorial. All right, now if we plug some more of those into here, this was x to the 4th. X to the 5th would be 1 over 5 factorial x to the 5th. No x to the 6th minus 1 over 7 factorial x to the 7th. So if I bring down all the non-zero stuff over here, we have 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. Now, I am going to go plus dot, dot, dot. Maybe we can come up with a pattern for this. I want to write this as a summation. Now, almost always our summations are going to start at 0, so we're going to have to kind of figure that out. Let's start with the first thing. Here we can see that it alternates, plus, minus, and we're going to assume, because we know what happens to the derivative here, that's going to continue, which means I'm going to have a negative 1 to a power. Now, for alternating, we're either going to put an n or an n plus 1 generally. Basically, do we want it to start at positive or do we want it to start at negative? Well, if n is 0, if I just put 0 in there for the exponent, that is positive and I want it to start on positive, so that should work. Okay, now notice here I have x to a power over something factorial. Now that's always the odd powers, or odd numbers, right? 1, 3, 5, 7, and the factorials match, 1, 3, 5, 7. So whatever the exponent is, we're going to have the same thing for the factorial. Well, to write an odd number, we take an even number, which is 2n, and we either add 1 to it or subtract 1 from it. So which one of these would give us what we want? Well, if n is 0, that would give us a negative 1 as an exponent. That wouldn't make sense. So let's see if 2n plus 1 works, and I'll put the factorial there in the bottom in a second. So if n is 0, I get x to the first. Good. If n is 1, I get 3. That works. Okay, so that should work. And we know that this on the bottom is the same factorial, which means I'm going to say that this sine x is equal to, remember that's my function, way back over there, is the sum n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. Okay, so there's a power series representation of our sine function. Now, if you want to know where this converges or diverges, you'd have to do find the radius or interval of convergence and do it. I'm going to cheat here and help you out. This actually converges for all values of x, finite values of x. All right, now we could do the exact same thing with cosine, but let's notice something interesting here. Think back to an old pre-calculus class when we learned about odd and even functions. We heard that sine was an odd function, and notice what did we end up with? We ended up with all the odd powers up there, and we know cosine's an even function. So kind of just think about this, if we just shifted everything one way, all this would be shifted up 1, so everything would be shifted over, so instead of getting the odd powers, we would get the even powers. So you might want to do this on your own to make sure that you can come up with this. But this is actually going to give me almost the same thing, except for instead of odd, I'm going to get evens. And we represent the even numbers by 2n. And again, I'm just stating this without proof, but this actually converges from negative infinity to positive infinity. Okay, so here's two basic power series that you may really want to be able to recognize or know what they are, because they're very, very helpful. And I'll show you here in just a second how it's extremely helpful in certain cases. Now remember, we're going to add this to one more that we already know, and I'm going to squeeze it in right here. We already saw this in the past, the sum n equals 0 to infinity of x to the n over n factorial. This was e to the x, and we showed that this converged for all values of x as well. So now we have three power series of three basic functions that we know, that we should know just kind of off the top of our head. Now, why would it be beneficial to know a power series off the top of your head? Well, let's say if I change things just a little bit. I'm going back to my original question here. What if I said find the power series not for the sine of x, but if I said for the sine of 4x? Well, you could do exactly what we just did. Take all the derivatives, evaluate it everywhere, find all your coefficients, plug it into here, find the, excuse me, find the pattern and write that pattern as a power series, or you can do this. We know that the sine of x is the sum n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, 2n plus 1 factorial. And then you got to remind yourself, remember x is anything. So I can replace x with 4x if I want to. So sine of 4x would be sum n equals 0 to infinity, negative 1 to the n, 4x to the 2n plus 1, all over 2n plus 1 factorial. And it took you no work at all, other than knowing the power series. Or you could make it more complicated. What's the sine of x squared? Well, you do the exact same thing. Sum n equals 0 to infinity, negative 1 to the n, x squared to the 2n plus 1, all over 2n plus 1 factorial. Now, I know those last two can maybe be simplified or messed with a little bit, but there you go. So by knowing a basic power series, it comes very, very handy when you're trying to do kind of like a modification of those. All right, another way that we can find a power series, which doesn't always work out real well as far as actually writing it in a closed form. Now, what I mean by a closed form, or if you hear somebody say a closed form, generally this is somewhat closed. You've written it as a pattern. But if I just wrote a power series like this, if I just said 2 plus x minus 1/3 x squared minus 1/5 x cubed, and I just wrote a bunch of numbers, this is not really closed because it goes on forever and you haven't really established a pattern. Sometimes finding a power series, we can write it in kind of expanded form, but it becomes very, very difficult to try to do it in a closed form. Here's what I mean. Let's say we say the same direction, find a power series. Well, let's let our function be e to the x. Let's do cosine x here just for fun. E to the x cosine x, and we want to center this at 0. Well, even though I put a center there, we're not actually going to be able to put this into a closed form. What you can do, though, is you can start multiplying two polynomials. Let me put them over here real quick, just as a quick reminder. Our cosine was n equals 0 to infinity, negative 1 to the n, x to the 2n factorial. And I know e to the x is the sum n equals 0 to infinity, x to the n over n factorial. Well, if I start expanding these out, so I'm going to start expanding this out. I'm going to put in 0, I'm going to put in 1, I'm going to put in 2. If I put in 0 to this, I get 1. If I plug 1 into there, I get x. I get 1/2 x squared, then 1/6 x cubed, so on and so forth forever. All right, now I got the dot, dot, dot. That's what's really going to make this tricky. All right, then let's start expanding out the cosine. So if I plug 0 in for n, that's going to be 1, x to the 0 is 1, 0 factorial is 1, so that's just going to give me 1. If I plug 1 into here, that's going to be negative 1, x squared over 2 factorial. So that's minus 1/2 x squared. If I plug 2 in there, that's going to be a positive 1, x to the 4th over 4 factorial. So 4 factorial is 24, x to the 4th minus, the next one will be minus, it alternates. And we end up with this. Now, how do you multiply this out? Well, not very easily, to be honest. Here's a little tip that may help you. I'm going to make some columns to help us combine some like terms. We're going to have a constant column, then x squared, x cubed, x to the 4th, and I mean right that plus. And that's plenty for what we're going to do. Okay, so some of this is going to require you just to kind of reason out how we're going to do this. Let's say, if I start distributing these polynomials, remember what we do? We take every term over here and distribute it over there. So you got an infinite number of terms times an infinite number of terms. So, fun. How many numbers can we get out of this? Well, the only way we can get a number is if we multiply this one times that one. So our only number out of this is just going to be 1. All right, can I get any x's? Now, basically what you got to do is look at it multiplying both different ways. If I take this 1 and multiply it over here, can I get any just x's? And the answer is no. If I move over here, if I take this and multiply it over here, can I get any just x's? And the answer is yes. This times this would give me an x. Okay, move over to the next term. Can I take this and multiply it anywhere over here and get just an x? And the answer is yes, but we already did that, right? We did that times that. Okay, that's the only way to get an x. That's the only x. Can we get any x squares? I can get an x squared if I do 1 times this, so that gives me a negative 1/2 x squared. If I take this x and multiply it over here, that doesn't give me any x squareds. But if I take this and multiply it over here, that does give me an x squared. It gives me a positive 1/2 x squared. So those are the only x squareds that we can get. Can we get any x cubes? Now you're going to start to see that it gets more complicated. 1 times over here, well, those are all even powers, so I can't get any x cubes. I can get an x cubed by doing x times negative 1 over x squared, so that's negative 1/2 x cubed. That won't give me any more x cubes. If I move over to this x squared, that would be x squared, nope, that doesn't give me any. But this one, if I distribute this, that will give me another x cubed, so it gives me 1/6 x cubed. Okay, so you're starting to see how messy this can be. So what you do is you write out a few more. I'm actually going to, for time's sake, kind of stop right there. You write yourself out a few more of those maybe, and then you just start adding your columns. So we would have 1 plus x plus no x squareds. Now we don't need to write that, but I'm going to. What are we going to have here? Minus, let's see, 1/2 minus a 6, that's 3/6. So that's going to be minus 1/3 x cubed. And we're going to say, okay, that's going to continue to go like that. All right, now notice, if we really wanted to do this correctly, we have to try to write out enough terms to where we could recognize a pattern and then put the pattern into a closed form summation like this. Most of the time, the pattern is exceptionally difficult to figure out. So if you were to do something like this for homework, what I would suggest is write out enough terms, maybe so you have at least 4 or 5 terms listed here, and then check the back of the book, and if he has it in a closed form summation, run off the first 4 or 5 terms and make sure that you got those correct. Because finding that pattern can be exceptionally difficult sometimes. All right, so using our Taylor and Maclaurin series to find or polynomials to find Taylor and Maclaurin series is a great way to come up with power series representations of most of our common functions. So if you ever get stuck and the question says find a power series, you can always use the Taylor and Maclaurin series to find a power series. Write out all your derivatives, evaluate them at the center, find your coefficients, write out the polynomial, and try to find a pattern.